Hi جميعا, اسمي حسام ترمس. I think most of you were here last time. This is the second session, the AI Journeys Fundamental Series. Okay, today we're going to cover linear regression and a bunch of miscellaneous things related to linear regression. We talked a bit about linear regression last time. في حدا ذاكر شيء؟ Or about machine learning in general. حدا ذاكر شيء from last time?
Yes, the three types of.
صح, عندي graph, عندي points, I'm trying to find the line of best fit. بس أول شيء let's recap بشكل سريع what we did last time that's relevant for today. قلنا machine learning is split broadly into three categories of problems or three categories of solutions. Supervised learning, unsupervised learning, reinforcement learning. We discussed all three last time broadly. بس في حدا يذكرنا specifically supervised learning what differentiates it from other types of learning?
When you answer the data, you give the label.
Exactly. إنه لما I'm training the model, I give it the questions and answers basically. صح? Okay, we said supervised learning is then divided into other categories. For now, we're omitting the others. We're focusing on regression. Does anyone remember what regression is? Regression is this problem of trying to find a numerical answer. So when a problem requires finding a real number, then we call it a regression problem. Okay? And it's going to be clearer what types of problems don't require numerical answers later on. Okay? So just a quick recap, supervised learning is the type of learning where we learn from labeled data. So I give the model this data set, I give it all the questions, all the answers, and it learns from this entire data set. Okay? And other types of learning, we might not have the answers. Okay? And these are some examples of where supervised learning is applicable. Regression is a technique used when we're trying to predict a real number. So the output of linear regression or the output of regression problems is a real number usually. Okay? Just to make it a bit clearer, I'm going to give you an example where the output is not a real number. Let's say you have an image and you're trying to classify it as a dog or a cat. So such a problem, it's called a classification problem. It doesn't fall under the category of regression because we're not trying to predict a real number. Okay? And so we saw an example like this last time. We said linear regression is going to be this problem where we have a data set. The data set, in general, we're going to label the questions as X. And by questions, I mean inputs. So I have this input. This is what I know about my data. And this is the label I'm trying to assign to my data. So Y is called the label. Okay? For example, let's say we're trying to predict based on the volume of rainfall. I want to predict the yield of a certain crop. Okay. So I will have some values here, whatever. I'm just gonna write some random values. And for each value of rainfall, so here X would be my volume of rainfall, and Y would be the yield. So for each value of rainfall, I'm going to have a specific yield. Let's see here, 5, 3. So I have some values of yield, and I'm trying to learn this relationship between the X and Y values. So the way we approach it with linear regression. So first of all, this is the problem. Is the problem clear? I have these data points, and I'm trying to build a model which, given a new data point, let's say later on I'm given this value of rainfall, I'm trying to predict what the yield will be. Okay, this is the problem I'm trying to solve. The way I'm going to solve it is I'm going to model it as a graph. I'm going to plot the volume of rainfall versus the yield, and I'm just going to put all the points I have available. So I'm going to get this scatter plot. Okay? And what I'm going to try to do is find the line of best fit for this scatter plot. This is not actually a line. But whatever, just I'm gonna find the line of best fit. And then hopefully later on, whenever you give me a new value for rainfall, I can use this line to predict what the yield will be. Okay? And we talked about how this process is done iteratively. So we're gonna start with this scatter plot, and then we're gonna throw a random guess, just any line. Then we're gonna refine this line, then we're gonna refine it again and again until we get to the line of best fit. And today we're gonna go into details. We're gonna go into the details of that process. But does everyone understand the high-level image? Okay. Hmm? Yeah.
In the background music or something for you.
Okay, so before we get into the nitty-gritty details, let's actually motivate us. So why is linear regression useful? These are some examples of applications of linear regression, or regression in general. So let's say we're trying to predict the price of a house based on its area. This is a very standard example. We can predict a car's fuel consumption based on its weight and engine size. So in this case, our input would be two columns. So we have x1, x2. This would be the weight of the car. This would be the size of the engine. And then my label would be its fuel consumption. Right? Okay. Can anyone think of other examples? So I'm giving two numerical inputs and I'm trying to predict a numerical output. Or does it, the inputs don't even have to be numerical, or they don't have to be continuous?
Food.
Hmm?
Food.
But give me like the entire problem statement. What's the input and what's the output?
The risk of getting cancer.
Okay, risk of getting cancer, that's the output, the label, okay. So my output is risk of cancer. And what would my input be?
How much
Smoke.
price is that?
Okay, how much he smoked, let's call it smoke rate. Maybe this is x1, maybe x2 is their age, x3 is whatever relevant piece of information I have. So I can have a lot of features, and then at the end of the day, I'm trying to predict a single label, okay? And so I wanted to put this slide, I wanted to emphasize that all we're gonna talk about today is just a straight line. It's just y is equal to ax plus b, and usually instead of a, we use w. W stands for weight. So yeah, everything we're gonna talk about today boils down to a straight line, which is kind of fascinating because we're gonna get into some complicated things, relatively complicated. But it all boils down to finding the straight line that best represents my data. So let's take a step back. Let's go back to this first line we guessed. So I claimed we're gonna make a random guess for the line, and then we're gonna gradually improve it, right? So how am I gonna improve it? Any guesses? Any suggestions? I have this line and these points, and I'm trying to improve this line so it better represents my data.
Comparing the points I have, the data I have, to the actual line.
Okay.
So how far the data is actually from the line, I should refine the line to best fit this data.
This is exactly what we're gonna do. How can we do this concretely? So what exactly are we gonna do?
The distance
Exactly.
from
Take the
point-
distance. So for every x, let's say this is x equal to 0.3, and let's say this is y equal to 1. For x equals 0.3, the actual answer should have been 1. What my model predicted was closer to, let's say, 5.5. So the difference between my predicted value and the actual value is 4.5, right? So I have this notion of, I'm gonna take my predicted value, which we're gonna call y hat. We're gonna take y hat, subtract it from y, and somehow this value is gonna represent is it going to represent how good my model is or how bad my model is? So the more this, so the greater this number. So do I want to increase this or decrease it?
Decrease.
I want to decrease it. Okay. So this represents how bad my model is with respect to one specific point, right? But there is still something that's kind of off here, because let's say I have this point. What's the difference here? It's like 16 minus, let's say 6, so this is 10. But if I actually calculate this difference here, it will be minus 4.5. And do I care about the sign? So do I want to value this as a negative number?
No.
I don't, because you're off by 4.5. I don't care if you're above it or below, right?
Absolute value.
Okay, I can take the absolute value, but then the math gets kind of difficult with absolute values. It's more convenient to just square the numbers. Okay? So what we're gonna do is we're gonna take y hat minus y and square it. Okay? This will represent something we'll call loss. So our loss function is gonna be this. Loss of y hat y, the subscript I here denotes the ith data point. So if I go back to this would correspond to I equal 0, maybe this corresponds to I equal 1, this corresponds to I equal 2, etc. Each point is assigned a certain I, maybe based on its order in the original data I'm given. So I'm taking my prediction for the ith data point and the actual value of the ith data point. I'm subtracting them and squaring. This is my loss function. Does this make sense to everyone? Okay. Is this confusing, the hat part? This is a completely different symbol than y. So y hat is my prediction for y, but it's a different variable. Okay. So this is my loss function. So now I have a way of quantifying how bad my model is with respect to a specific data point. But we're still not there yet, because at the end of the day, I could make the line pass through a specific point. If I want to minimize the value of y hat sub I minus y all squared, if I want to minimize this for a specific point, I could get it down to 0. But what I'm actually trying to do is minimize it overall. So I'm going to have to define something new, which somehow is going to combine the loss of all of my points. Any idea, any suggestions on what we might use here? So maybe there's some, but if I use the sum, so you're suggesting I will sum this from I equal 1 to n, where n is the number of samples, or n is the number of data points. Okay, so if I do this, then the more points I have, the more likely I'm going to get a larger value of whatever this quantity is. But does this make sense? So the more points I have, I'm being penalized. But does this make sense? So do I, when I look at a line like this versus the same exact line but with more data points, do I expect it to perform worse in one of these cases? Like its value of the total loss should be the same. I don't want to penalize it just because there's more points. Right? Does this make sense to everyone? Why we don't just sum it?
Yes.
Okay. I don't want having more points to be a bad thing. That's the point. So what I'm gonna do is I'm gonna kind of take the average. Okay, but then I'm gonna divide the average by 2. And this seems kind of arbitrary. So it seems like I'm doing this because I want to. And it doesn't really affect any of the math. It doesn't affect any of the concepts. It's just something that basically gets cancelled out later. So it's just convenient to have at this stage, but the concept can be understood without it. So what I'm doing is I'm taking the average of my loss over all data points, and then I'm taking this average, and somehow I'm claiming it represents how bad my model performs on the data overall. Okay?
كمان هو فكرت إنه number of points تحت اللاين تقريبا يكون قد اللي فوق.
Okay, but let's say your data is kind of like this.
اوكي فهمت عليك. ما عادش تصير تظبط صح؟
Yeah, I'm just gonna give the example if anyone else is thinking about this. So,
for normal distribution بيكونوا بيشبه مثل اللي عندنا اياها.
like let's say you have this data, it's not always going to work out that the points, okay, let's actually do this. Let's say you have a few points that are up here, and then a lot of points that are down here. Okay? Then your line of best fit might look something like this. Because I wanna do good with respect to the entire data set, but these points, they're more, so they're gonna pull me down more. Right? Okay. So now I have two things. I have this loss function, which we denoted by L of
Y hat
y hat y is equal to y hat minus y whole squared. And then we have this cost function, we're going to call it J, this is how it's usually named, which is a function of, let's say for now it's a function of y hat and y, and it's simply the average or half of the average of my loss. Okay? And this definition is useful because I could choose any loss. I did mention that squaring is convenient, but in some cases we could take the absolute value. Okay? We could take it to the power 4, for example. We could do anything with the loss as long as it's positive, and then I could just average it. Okay? So this is the second equation we're looking at. And notice one thing. Well, this is the expression I just wrote down. Okay? And then what's y hat? Y hat is my prediction. Okay? And what did we say our prediction is? Just a straight line. So y hat is wx plus v. So I'm going to make this substitution. Instead of y hat, it's wx plus v. And xi again, because it's the ith entry in my data. And the rest stays the same. Is this clear? Okay. So now j, instead of writing it as a function of y hat and y, it's now a function of w and p. Okay? And why is this important? Because it highlights that.
The slope.
Sure, the slope is w. It highlights the slope, but it highlights a very important concept that if I wanna decrease the cost, we've agreed that our goal is to decrease the cost, right? So if I wanna decrease the cost, the only things I can change are w and p. Right? This is the only thing I can change. I don't have control over the xi's. I don't have control over the yi's. I have control over y hat by controlling w and p. So now, the problem of finding the line of best fit has become this problem of finding the best values of w and p. And that's it. If we find the best values of w and p, we would find the line of best fit. And I claimed earlier that we're going to do this iteratively. So for this line, there's a certain value of w and p. And then gradually, we improve w and p, improve w and p, improve w and p, until we reach this optimal line. Okay? And to understand how we find these optimal values of w and p, it's important to understand the structure of this, this cost function. So just to make sure we define things clearly, the loss function is this. It's basically the error informally, the error with respect to a single data point, and the cost function is the average of that error over all the data points I have in my data set. Okay? Does anyone have any questions so far? Is everything clear? Okay. So now I'm trying to minimize this function. The first thing one might notice about this function is that there's an element of, like it's all quadratic functions being added together, right? So again, this is a function of w and b. And I have something of the form, so xi's and yi's are constants. Do we agree on this? Because they come from this table, and this table is just a fixed table of values. So this is a bunch of quadratic equations being added together. I'm using the term quadratic loose here because it's a function of two variables. But anyways, I know this is always positive, but I also know that in 3D space, it kind of looks like this. Kind of like a 3D parabola. Okay? Actually, I'm going to show it to you. So this is what it looks like. Any loss function, in the case of linear regression, would look something like this. Like this. Okay? And which point am I trying to find on this surface?
The minimum.
The minimum. I'm trying to find this point. Right? Once I find this point, I'm done. I found the optimal line. So how would I find this point? Let's go back to something wide. Okay. So here's what we're going to do. Let's forget the 3D structure for now. Let's imagine it's 2D. This thing I showed you in 3D, what do you think it would look like if I want to squish it into 2 dimensions? A parabola. Okay? So it looks something like this. The same basic structure. So at the end points, it's very large, and at some point, not necessarily at x equal to 0. So for some value of x, it's gonna be it's gonna be at the minimum, which is also not necessarily 0. Let me actually read about this. So I have my axes, okay, and I have this parabola. Okay. What's my x-axis and y-axis? So for now, let's assume my model is y equal wx. Let's assume b is 0. So what does my x-axis represent? And what does my y-axis represent? So what am I graphing here?
This is the cost one.
The cost. So my y-axis is the cost. Okay? And what's my x-axis? My cost is a function of w and b, but in this case we assume b is 0. So it's a function of w. Okay? So again, by finding this point, I would have found the best value for w. Let's call it w0. The way I'm going to do this is I'm going to start at a random point, and at every point, I'm going to calculate my gradient. Is anyone familiar with what the gradient is? Anyone else? Okay, basically a gradient, intuitively, is a vector that points in the direction of greatest increase. So if I'm at this point, my gradient at this point is going to be a vector that looks like this. So it's telling me if you go in that direction, the value of the function will increase. Okay? If I'm at this point, for example, the gradient would point in this direction. Does this make sense?
Yes.
So now, given this, I know the structure of my cost, and I know I have this gradient. Can anyone suggest how we might reach the minimum? Okay, so I'm going to take minus the gradient. Minus the gradient would point in the other direction. So if the gradient points in the direction of increase, it's minus the gradient would point in the direction of decrease. Okay, and now what? So I have minus the gradient. I'm going to go in that direction, right? So the gradient is telling me go to the left to increase. So I'm going to go to the right. And I'm going to take a very small, so right now let's say I'm at x, let's say I'm at W1, W1. I'm going to take a very small step in the opposite direction of the gradient. So let's say I jump to here, to W2.
You keep doing that until the sense varies, so we know that we reached the minimum.
Until what?
The sense of the gradient varies.
Okay, so I'm gonna keep doing this. Okay? I'm gonna keep making small jumps until I reach the minimum basically. Okay. And how do I detect that I reached the minimum? Either, as you said, the gradient starts switching direction, or the gradient becomes very small, right? Okay. Is this making sense to everyone?
Yes.
And this only works because I know my graph looks like this. Let's say my graph looks something like this. Then why would this not work?
it would change this انه it wouldn't be that.
Because
Exactly.
it could
So
be
I can't claim that I'm finding the best line if the graph looked like this. Because say I start at this point. What direction is my gradient?
Right.
This way. My gradient is in this direction. So what direction am I going to go? Left. I'm going to start making small jumps all the way down till I reach some minimum.
but this is not the best.
This is not the global minimum. This is one of the problems with this algorithm.
We can slice.
Hmm?
Slice كل واحد.
As how do you know كل واحد يوم? How do you know where to slice? One approach would be just start randomly at a point and find the minimum. And then start randomly at another point. Maybe you start here. And then maybe the next time you start here. Maybe the next time you get lucky and start here. So run this multiple times, and then hopefully one of your runs would find the actual minimum. This is one approach to fix this problem. But in this case, luckily enough, we don't have to worry about this. We know in linear regression that this is our loss function. It looks like this, it's very clean. If I start at any point and I apply this process of taking small jumps, I'm going to reach the minimum eventually. Okay? And just so we can see how this looks in 3 dimensions. Okay. So this is my j, my cost function. Yeah, this is not, ignore these things. These are just to set it up. But just focus on the actual geometry. So this is my loss function. Okay? I'm trying to find this point, the minimum. Okay. Can you all imagine how this looks? It's kind of like a ball. Yeah? So now instead of having only W0 and W0 determines my cost, now I have 2 things that determine my cost, which are what? W and P. So previously when we worked with this example, we assumed P is 0. Here we're not making that assumption. So we have some value of W and some value of P. Okay? And then if I basically extend these lines, wherever these 2 lines, the line parallel to the W axis, intersect with the line parallel to the V axis, I would go up and I would reach a certain point on my j. Okay? And you don't have to focus on these details, but basically what I want you to understand is, for a certain value of W, and a certain value of B, I have one single value on my loss function.
Yes.
Which makes sense. If I give you one line, it's only going to have one value of cost. You're just going to do the math and you get a specific value of cost. So for 1W and 1B, I get a value of my cost function. And now, if I draw this gradient, the gradient is going to point outwards. Okay? And so I'm going to take the negative of the gradient, and you can see that it points towards the center. Right? You can see it's pointing to, if you follow the gradient, you're going to go down there. I'm trying to find an angle that shows this, but hopefully you can see it. So if I'm standing at this point, and I go with the gradient, I'm going to end up going down. Okay? You can view it from above, you can see that the gradient, wherever you place M, you can move M around. Wherever you place it, the gradient points downhill. You can see it from a different angle. Let's say I place M here. Sorry, not the gradient. The negative of the gradient is always going to point downhill. Okay? So what I'm going to do is I'm going to take small steps in the direction of the negative of the gradient until I reach my minimum.
You the gradient outwards صح؟ يكون outwards.
The gradient will be outwards. بس أنا اللي عم برسمه is the negative of the gradient.
I have a question. Can you somehow use calculus to find the minimum?
You can. That's determinate. So basically you're saying, you know, I have this data, how can I, in a deterministic way, just find the minimum?
Yes.
This works when you have only W and B. But for larger dimensions, so if you go back to this example, for more X's, I'm gonna need more W's. So at some point, I think instead of having WX plus B, it's gonna be W1X1 plus W2X2 plus B. And the more dimensions you have, the more computationally expensive it is to actually find the minimum deterministically. And it turns out that this algorithm gives us a good enough approximation. Okay? So let's actually write down what we came up with here. Okay. So let's say an iteration T. So this is an iterative process. There are multiple iterations of me improving my W. Multiple steps of me improving my W. So let's say at iteration T or at step T, I have the value of W is WT. Okay? What would be the value of W at T plus 1? So at the next iteration, what would the value of W be?
Moving downwards or up.
Hmm?
I'm moving towards the minimum.
Right. So it's gonna be, first of all, I'm moving towards the minimum, meaning I'm starting at WT. And then I'm adding something. Right? I'm starting at wherever I am right now, and then I'm going in some direction, so I'm adding something to my current state. Does this make sense? Okay. And what am I adding? Hmm? I'm adding the gradient, basically. The component of the gradient that's the W component of the gradient. So the gradient is a two-dimensional vector. It has a W component and a B component. Okay? And I'm adding the W component to W and the B component to B. This component is denoted by this symbol, and we don't have to worry about what this means. But basically, what I want you to understand is this comes from the gradient. So by adding this to W, I would be going in the direction of increasing the last one, right? So instead of adding this to W, I'm going to subtract it from W. So I'm going to add its negation, let's say.
Isn't that like the derivative?
This is kind of like the derivative, yes. But so we're not going into these details. For me, like what I care about here is this comes from the gradient, and by adding it, I know that I would be increasing my cost. So by subtracting it, I know that I'm decreasing the cost. Okay? And the intuition is here. Again, if I'm starting at this point, the gradient is going to be in the outward direction. So by going with the gradient, I would be climbing up. By going opposite to the gradient, I would be climbing down. Okay? But this is still not enough, because I also want to control my step size. So let's go back to this 2D example to understand this. Let's say I start at this point, okay? And my gradient points outward, so I go inward. And then at this point, my gradient also points outward, but I take a very big jump, and I end up here. This is a problem. If I take big jumps, this is a problem. And let's say at the next step, I end up here. Then I end up here. Then I end up here. So I'm going to keep oscillating, never actually reaching the minimum. And the problem here is my step size is too big. So I want to control my step size. So we're going to call this step size the learning rate. And why do we call it this? Because it controls the rate or the speed at which you're learning. If you take small steps, then you're learning slowly. If you take big steps, then you're learning quickly, but you're risking...
Less efficient. Less efficient.
Which is less efficient?
The bigger steps. You might miss the minimum.
It's actually, Like you can actually view it as being more efficient because I'm taking bigger jumps towards the minimum. But yes, I'm risking skipping. So it can cause a problem in like actually reaching the minimum. If I make the learning rate very small, I'm guaranteed I'm gonna reach the minimum at some point.
That's more conditional.
But then I'm taking very small steps. It's gonna take a very long time. So I have to find this sweet spot between setting a learning rate that's small enough so I don't skip the minimum, but at the same time I don't want it to be too small and I'm standing here all day waiting for this one line. Okay? Do any of you have any questions so far? So just to complete this idea, so I'm gonna subtract alpha times this gradient component, and alpha is the learning. Okay? Does anyone have any questions so far? Okay, so just to quickly recap what we did before we move on. We said we're starting with some graph. Okay? Actually, I have this. Okay. We're starting with some graph. Throwing just any line on it. I'm throwing out my guess. And then, what's the first thing we define? We define the loss. And what's the loss of yi hat yi?
Absolute value of one half,
Square.
one is absolute square.
Yeah. So I either for our case we're just gonna square it. So it's y hat minus y all squared. And then what's the second thing we define? We define our cost. So it's a function of w and d. And it's equal basically to half of the average of the loss. Okay? And you can substitute this here, and then you substitute, instead of y hat, you substitute the actual line. Do you want to go through this now, or is it clear? Okay. And then we said that now that we've reached this, I'm trying to play around with my W's and B's to minimize this expression. And we basically discovered gradient descent, which is this process of finding a gradient, of following the opposite of my gradient gravity. Okay? And I'm just going to show you the equations involved in gradient descent. Okay? So for now, let's ignore these. Let's just focus on the top part. So I have W of t plus 1 is W of t minus alpha times the W component of the gradient. This is exactly what we did here. Alpha is the size, it controls the size of my stem. We call it the learning rate. Okay? So usually alpha is a number less than 1. Usually it's like 1 over 10 or 1 over 100 or 1 over 1000. It's a very small number usually. But again, not too small. Because you don't want to wait forever for a model to train. And for B, it's basically the exact same thing. I'm training W and B using the exact same approach. So B of t plus 1 is B of t minus alpha, and the B component of the gradient. Here was the W component, here it's the B component. And you don't have to worry about the notation. It's not important for our purposes. Yes?
C is the number of iteration.
T is the teeth iteration, yeah. It's like I'm currently at the teeth iteration, how do I find my value? Or actually I'm currently at the t plus 1 iteration, how can I find my value based on the teeth iteration? Okay? And these equations, they basically come from what you mentioned, which is taking the partial derivative of the loss function. So this should be J actually. So of the cost function actually. So if I take the partial derivative of the cost function, I would get these expressions. Okay? Yeah, that's basically it. Any questions?
Why did I square the losses in
No, ما رجعنا عشان هون. Okay, what would you do rather than square the loss? Then you would do, then basically you're doing the absolute. صح؟
انت اوريدي هيك حطيتها سبوت.
Okay. And you're saying let's instead of defining the loss as the square of the difference, we define the loss as the square root of the square of the difference. Huh? Okay, this is basically the same as the absolute value of the difference. Can you see why? Okay. But this is the absolute value, and this is completely valid. You can do that. But then, when you're trying to calculate the expression, the components of the gradient, it gets a bit messy. So you have to take the derivative of the absolute.
بس انه السكوير ما فرق شيء.
No, the square, okay, is okay, let's say I have this expression, wx, this exact expression, wx plus b minus yi. This is xi. And these are constants. Yeah? These are constants. And then I square this. If I want to take the derivative of this, how do you take the derivative of this? With respect to w. Because I want the w component and the b component. Let's say for now we want the w component. 2 wxi plus b minus yi. بعدها بضرب الديريفيتيف of this. Derivative of this with respect to w شو هي؟ هي xi. Okay? I got this. هيدي إذا تعمل لها سكوير. Let's say تعمل لها absolute.
Some points it's not.
I have to take the derivative of this. Keep the derivative of the absolute. It gets messy. It gets messy. كيف؟
سؤال
ما جاوب.
ايه بس انه الصور عندك كيف خطرنا نصير سكوير؟
لأنه you want to force it to be positive.
ما بدكش بس هيك مثل ما بدك انت تريد الديستنس بين تو بوينتس بس تاخذ الابسولوت عم تحكي عن كوب هيك نعم طلع هيك كيف؟ when you take this انه distance صح distance point نحن اصلا when الحساب بلش يوصف regression points عم يحكي عن distance what is the distance؟ هي square of the distance بس يعني هو مش بس هيك وكمان وصلت للمسنس يعني بس the error of being it's valid and sometimes we actually take it مثلا انه when you do the square تخيل عندك رقم صغير جوا لا رقم جوا كبير فكأنه اللص حيكون كثير كبير يعني هيدا penalizes شو اسمه loss square بس هيدا it's not too يعني منه كثير حساس للرقم الكبير يعني هذيك بتحط رقم كبير عند السكوير بتصير اكبر كيف بس هيدا لا sometimes اذا انت بتتوقع انه يطلع عندك ارقام كثير كبيره you would use the square and you would مثلا you would use the absolute value even though it's showing us but it depends on your use case.
يعني again this is completely valid. You can do this. بس انت عم تسأل انه this feels random. It doesn't. It's not really random. And if you think about it, as you reach this point, let's say you reach this point, you want to force this to be positive, but you know you're going to take the derivative later on. But you want to do something to this to make it positive, but at the same time make the derivative easy.
They were doing this. At some point they knew they were going to do the derivative.
Probably, yeah, probably.
هو انا agree with you انه sometimes هذا بس تعلم كثير اشياء بس هيك عم يعملوه and then somehow they work.
Yeah, but I would guess انه they know at some point they were taking يمكن they took the absolute. بعدين when they reached this point قالوا خيي لا. Let's
One
just.
of the was explaining to me he made us derive the distance formula من dot product. ما بعرف شو بين الداتا بس هو
هلا حتشوفي كثير اشياء هيك.
كثير ايه.
هلا حتشوفي كثير اشياء. You
One
try
other
to
thing, by the way.
and then let's go.
One other thing بخصوص هاي. لما قلنا هيدي التو it feels a bit
ليه
random.
سبب؟ انه هيدي كمان التول اللي
Exactly. Advanced starting point.
Okay. هيدي التو بس لايش اعمل derivative ل this thing it cancels out. فكمان this felt random. بس انه اللي حط هيدي التو probably he knew شو حيصير بعدها.